Madam is principal in MSN campus, Adikavi Nannaya University, Kakinada. Coming to Madam's educational qualification, Madam has completed Bachelor of Technology from B.R. Siddhartha Engineering College, Vijayawada, and her master's.
Challenging thing is, in this workshop, I see my friends from zoology department and management departments. So the challenging thing is, by the end of this session, I don't know whether they will understand this or they create, whether I can make them create interest on this or will they run away, I don't know. Yes, my title is like the Introduction to Vision Transformers, Neural Networks for Text and Visual Classification or Processing. This is just an extension of the morning session introduction. Morning you had what actually is a transformer, and I'm going to focus much on how a transformer works. Though the title is Vision Transformer, but my focus will be much on how a transformer will work for the text and a little bit introduction of Vision Transformer and how it works for the images. The total slides will be of just the introduction of what a neural network is and why do we call the transformer 2 as a neural network, and how it comes into the deep learning concept. And then we'll see the math behind the transformer, what actually happens inside. Morning we have seen as it is being called as a deep learning, so many layers in between. What actually happens inside those layers, what are the mathematical functions. And then at the end, if time permits, we will see how it implies or implements in the Python language, how we can able to predict the text and how we can classify or how it gives the summarization of any image. This is what my session will be is. So just with the first slide, we can say this is all the index, and we'll try to see the contents of this session also. This that is what the final transformer output will be. We'll see what that is. Different types of neural networks. Morning also we had the same summary, just what is neural networks and naming of them based on the types of the neurons and the layers, how they are. Yes. And the base thing nowadays, we always see this convolution neural networks, and I think students now started learning what these convolutions are and what are the operations each layer and the math behind that. This is just the base for the transformer. So I just saw only this figure just only for the visual sake I have kept that, but our focus is not on CNN. Our focus is on a transformer. So this is just the CNN, but you might be having, you can just focus on the pooling and the fully connected layers are, and the red dots implies the classes. That is just the base thing. Just for the interestingness, we'll start with the small math, very simple math, how to find the similarity between two documents. Morning session we said, like if we take the cosine similarity, which finds the similarity between two documents or the similarity between the angle. Angle is nothing but it comes between the two vectors. So when you take that angle or when you take the vectors and what they are, in how they are placed and based on the magnitude of that vectors. So if we take A and B there, yes, A and B there, they represent the vectors, and we say that the vector basically we start it's nothing but which consists of both the direction and the magnitude. So if we multiply two vectors, we'll be getting a scalar, but here when we see the magnitude denominator and A and B, we take that to be as two vectors. And the dot product of the two vectors, when we do, if we do that one as the transpose of the dot product, we get the scalar of those two vectors will give some value, and that value indicates what is the difference between those two documents, because we get the difference starting from 0 to 1 based on the value we got out of it. We can tell what the difference are. If we see that angles there, generally for cos theta, we know that if it is cos 0, it's a 0 angle. we say that they both are very similar to each other, which indicates if both the vectors does not have any difference in between them, if both of them does not have any difference and if the angle is very zero, which indicates they both are very similar. If the other vector is having much difference variation, they are not similar to each other. So that is what is. Though there you can see the cosine similarity between the two vectors. So the focus is on x and y, and if the cos theta angle is 0, they are both are very related. If the angle is very large, they are not related. Document representation, one we have seen, which is one hot vector or one hot encoding also we can say. So representing each word with 1, if it is not there, if that's in that sentence, if it is not there, 0, and we are building two vectors here. So D1 is one vector, D2 is another vector based on the two sentences. The best data science course and the data science is popular. So we have the common words in these two things, and we need to find the similarity between D1 and D2. Representing that text with one hot encoding vectors, we try to find the difference by taking the sine, cosine here. So that is what the formula here, and so finally those two are related with 0.44. So which is 44% similarity is there, and the inverse of that cos theta is r cos, which is 63.435, just 43 and inverse of that. So this is the simple introduction or simple math, how to find the similarity between two documents with the simple technique behind one hot encoding. Just the simple introduction. Morning we said like we are taking the weight matrices, like when we consider a vector, random, actually it is set as random, but we can define the vector instead of the random numbers. If you pay the attention here, just if you pay the attention here, if we take a vector here, instead of one hot encoding, if we want to take the values between 0 and 1, we can define the features of the vector. So based on, here if I am there as my name as Kamala. So to that Kamala, you define what the features are. So what is the gender here? What is my profession here? What is my place here? So on. You can define the features of the vector. You can even say the dimensions also. So that the dimensions you can define and give the value to that, which makes that to have some parameters to that vector. I hope you are able to understand. If you see the figure there, we have a cat and checking whether it is the living being. If it is a living being, you can make it as 0 to 1 values. So you can give 0.8 or 0.9. If it is a feline, which belongs to the cat's category, human, it goes only 0.1 or 0.2 because it is not human. And the gender, royalty, verb, plural. So these are the features we can define for a vector. If it is not a one hot encoding, if we want some real values between 0 and 1, you can define what the features are. Based on that, you can give some values. So in such way, instead of randomly, you can take the values of the vector based on what the features are. So on the right hand side, if you see, and see how many dimensions we are having. Altogether 7 dimensions are there, and if that 7 dimensions are to fall onto the reduced dimensions, which is 2D, where we are taking only x and y. So we calculate all those values and say that if you take the values of cat and kitten, they both fall very near, cat and kitten, whereas the dog and houses, they are far. The dog and houses, those values are far, these two are near. So which says that cat and kitten are similar and dog and houses are dissimilar. So this is what the representation, how it falls. And visualization of the embeddings, this is what we say like whatever values we give to the vectors to the words based on the feature weights, we call that to be as the word embedding or input embedding, which is very, very important in the transformer architecture, which is the starting architecture, starting layer. And the relation, when we are forming the relation, if you see the second picture, the man and woman and king and the queen, though they are far, they are represented or they are, we had a dotted line which indicates that there is some relation between them. There is some relation between the king and the queen and a man and a woman. So it is like we are going to find the similar words, still I did not go for the context here, but just only the similar words based on the meaning and whether any relation exists between them. Here comes the context. The relation in the sense in what they are related, so we have to focus on the context. How to do all this, we will see. Yeah, so what is basically a transformer is, and we know one transformer till now, and the other transformer, Morning said, all our kids will know what the other transformers are. And last 3 months back, when I'm applying for some project, idea building project, there I'm trying to see whether any other method which is better than CMM. Then I have come across, when I first saw that word vision transformers, what is this word? What is vision transformers? Why a transformer is playing a role here? I was a bit confused and it's an anomaly there. But later, yes, as Morning said, we are just transforming our one context to the other context. That word is app. So we need to focus. By the end of this class, we shall see what actually this transformer is and how all these layers will work out. So we can define the notations. What we see here is we should be knowing all these notations so that we will know how the working principle goes for this transformer. So queries and keys, values, all the position embeddings, word embeddings, what is attention, self-attention, multi-head attention, and encoder, decoder, what are the softmax layers, feed forward, and now all these notations, we will see everything, and then we will see the working of the transformer. Yeah, I mean, like, we can take whatever I tell for transformer, you can even take it for a vision transformer also. So why we need. So the morning, we have seen, if you take one language, if you take from one language, you can convert that with the transformer. There are so many applications with the transformer. We'll see in the next slide. And the other application is like the training or dialogue completed. If a question is given, answer should be given by the transformer, or if the answer is given, question should be given. And if you take the vision transformer, how we can classify the image or give the summarization of that image, give another images of that same relation. That is with the vision transformers. Yeah, why I said this is not for the vision classification. The most 3 CEOs there, Elon Musk and the person who invented or the founder of OpenAI, Sam Altman and Sundar Pichai, heavy competition between them. Elon Musk said, like, the ChatGPT is a scary good one, ChatGPT. And the founder, he himself said, like, ChatGPT will remove many jobs. It is like it is going to replace so much of manpower. And Sundar Pichai, actually, when we remember Google search, we remember Sundar Pichai. Now it is the challenge for Sundar Pichai, instead of Google search, people has to go for Google Dance. So Google Dance expects more reliability, more accuracy, leaving the unnecessary things. So that is the challenge for Sundar Pichai. Instead of Google search, people has to go for Google Dance. And here comes the ChatGPT. Actually, my system did not get connected. I was using the formation or the formal thing of ChatGPT in my system, I gave the question yesterday, who is the Vice Chancellor of Radhika Vinana University? I wish I could show that, but it is not connected. And as Morning Himabindra has said, like it goes in a conversational way. The answer given by ChatGPT is, as I'm not a human and not updated currently, as far as the information I got, Professor Mokka Jagannath Rao is the Vice Chancellor, which indicates that it has given the past data. It is not giving the current data. Scholars, those who are here, yes, you can do. And another confused thing morning I got is, I asked what is the largest university in AP. It gave, as per the students' record, Andhra University is the largest university. I said, because it said as far as the students are concerned, so I asked the university with the more affiliated colleges. Then it gave JNUK with some 350 or 300 affiliated colleges. I asked the question, number of affiliated colleges to AKNU. It gave 400 plus 400 affiliated colleges. Then I asked the question, then what is the largest university in AP? Then it combined that two sentences, JNUK is 300, AKNU is 400, the largest university is JNUK, it's a ChatGPT. Lot of research has to be done on ChatGPT here. It is not even comparing the answers what it has given. It is just blindly telling, still though the numbers it has calculated as 300 and 400, but still it says JNU is the largest university. So how to overcome all this with our research? It's not yet updated yet. How we can define what a transformer is? As I said, like the before picture shows, you have the encoder and you have the decoder as the major two modules, but inside you have so many layers of that vision transformer or the transformer. And I said, like attention mechanism is more important. As in the 2017 paper, the title itself is all you need is attention. Attention is all needed. From there the attention word started. So from the attention, self-attention to the multi-head attention. So now we are just increasing the attention ways. Some people say that it is a self-attention mechanism, transformer. And that is an example of a deep learning because it has more number of layers. We can say, I felt like the definition for the transformer by combining all this is, it is an iterative process to analyze text or images with embeddings, word and position embeddings, and self-attention mechanism for high efficiency throughputs. This is what we can define what a transformer is. So as of now, you might have got an idea of what a transformer is, nothing but it is just a mechanism. It is just a set of layers to have high throughput and by taking the text or the images. Images, just make that word replace to as vision transformers. Morning, yes, we have seen the different popular transformer-based models. I said, like with so many layers, some can have only few layers, some can have only the encoder, and some can have only the decoder. Based on that, the name conventions have gone. So different things, and yeah, that ChatGPT, like the generative pre-trained transformer, we have the versions of it. Now at present, Google, we always give the text. We always give the text. I always think, why not we give an image and ask the Google to search? So there comes the DAL. He took the name, it's like the Spanish author and the Walt Disney. So full names I wrote somewhere, I forgot what there. And this is of the text which are for the birth, and we go for the text classifications, we go for the text prediction, we do the speech recognition or named entity recognition. So many applications are there. Yes, the very low level of transformer framework you can tell is give the inputs and get the outputs with encoder and decoder in between, considering the features. Just that is the very low level framework. And how does the ChatGPT work here? Now you can say that words here, it's a pre-training is there. We are having the transformer and then we are going for this ChatGPT. So we'll see in detail what is pre-training and fine-tuning. As morning session is said, pre-training is nothing but totally consider the total data and then take the sub-part of that trained data. Of the trained data, take only the sub-part and apply that on some other data to check, which is the fine-tuning. We also call that as pre-trained data. And by passing all these layers of the transformer, then you get the output of this ChatGPT. So we'll focus on what is a transformer and what the layers are by considering with some examples. Again, see the words here. This is the embedding. You can take this embedding as input embedding or word embedding. To that, position embedding is there. And then we have multi-rate attention, add and norm. Encoders, you can keep any number of encoders you can keep in your transformer. So which is like you have some number of layers you can keep. So you can embed 4 or 5 encoders, you can embed 5 or 6 decoders also. So morning it's been said like up to now only 8 encoders are there, but we can increase. We will see this again, we will see this architecture again. This is what is the theoretical part of what a transformer is, what are its applications and what are the different forms, what are the notations we have seen. Only till now we have seen what we have seen. Now we will see the math behind every layer in the vision transformer. Before I go, YouTube for this transformers. 3 series are there. All the 3 series are very important, but we need to work out little bit we need to work. So I can do AI. Yes, if you take one simple example of the transformers, if the input is something, not that woman Cersei, I think she is Cersei. So when you play the Game of Thrones, that is the first part of the sentence, the completion of that sentence and what we expect from the transformer is the transformer has to complete by saying you die or win. There is no middle ground. That's what the transformer should complete when we do that first part of the sentence. So how the transformer will do, and basic thing is whether it is the deep learning, whether it is the data mining, whether it is data science or the transformer or the vision transformer, we all should know or keep in mind is we give the huge database, the raw data as input to our transformer. We have to make ourselves aware that transformers or whatever the concept we take, huge database is given as input to the concept what we are thinking here. So when we take here the text inputs here, when you play the Game of Thrones, because the transformer has to deal with the numbers, so that when you play the text of play the Game of Thrones has to be converted to the real numbers. So we can take the real numbers to as vocabulary data dictionary and assign the numbers to each word. And here it is shown like only few words are highlighted, but how many number of words are there? All that words you can give some IDs to the numbers and consider, which is a long process. That is the purpose we need to convert them to the vectors. We will see here. Yes, here comes the how we treat. This is the first part here. After we have to go for the input embeddings. So we have the vocabulary here, vocabulary words, and those are to be converted to the vectors. Now we have to consider when we say the vectors, you have to give the size of the vector, which is nothing but the dimensions of the vector. So the vector you need to represent. So when you say the word when is there, you have to represent that with the five dimensions vector. The values here, no need of random, as I said in the beginning, no need of random. You can define what each dimension is, and based on that dimension, you can fill the values of the vectors. So as of now, you understood how a word has been converted to a vector. Word where the initial part is we have taken the vocabulary ID, and that vocabulary ID has been converted to the fixed dimension. In the picture it is only 5 dimension, but basically if we take the words, it can go up to 512 dimensions. You can imagine the size of the vector here is 512 dimension means. So we can go up to 512 dimensions. Yeah, that is what is linguistic features 1, 2, 3, 4, and 5. You can define what these linguistic features are and then give the values to those vectors. And if we see that here, and if you have the hyper dimensions in space and where you place all those vectors, and you get some the play and the game, they fall into one quadrant. And if you see this, the other part, they are trying to move this one. That is what is when you make the positions of that vectors, they move a little bit nearer. The former one is the word embedding. The former one is the word embedding, where they are related to each other, where they are having some context, or where these are the linguistic features of the context we define, and with that they fall into similar quadrant. And if we again on top of it, if we calculate the positions where they fall, they move a little bit closer. So these two we need to find: word embeddings and the position embeddings. So the input embeddings here, which is nothing but the word embeddings. If you take the vocabulary and then having the vectors out of it, this is the input embeddings. And in that, as like morning, all the words fall at a time. All the words, in the sense, into the transformer, we feed all the words into the transformer, and we are not giving any orders to that. So to get that order, we need to have the position embeddings so that they become a bit more nearer, these words. Yeah, similar to the example here, even though she did not hear the word not plays different meaning in the first and the second sentences. So we need to calculate the vectors for that word and the meaning and the relation between them. So to that word embeddings, input embeddings, we have to add the position embeddings. E plus P, both we have to add. And then we get, after that, we get a vector for each word, and the magnitude of that vectors will give which vectors are nearer to each other. Are you able to follow? Are you able to follow? So we are calculating embeddings, input embeddings, position embeddings, which gives the EP embedding, word as well position embeddings, which is the vector for a word, and the total calculation of the vectors altogether gives which vectors are nearer to each other. How to calculate the position embeddings here? So in the position embeddings, we don't know the values, we have calculated only this part. And with the position embeddings, now the first example what I have taken as cosine similarity. We can even take the sine similarity also, just dividing the words which are in the even, go for the sine similarities, the words which are in the odd number, go for the cosine similarities. We can take all the words cosine similarity also, no problem at all, but for more effectiveness, they have changed that cosine and sine functions to get the more values, considering the errors, considering the, what I should say, more accurate values. So both the functions are considered here. So position embeddings is for the sine and the cosine. Now the parameters there inside, position is the word vocabulary position, and T is the set of dimensions, and I, it has to go for the indices of that vector, that is the I part here. So P1 is the position, this one, and T is for the number of dimensions and I is for the indices. So how to fill these values is, yes, if we draw the cosine graph, which we call that as sinusoidal graph or the cosine graph, if you take when I is equal to 4, say for example, we get some graph like this, and these values, because they go for the values from -1 to +1, and on the x-axis we take the positions, word positions. At word position 0, we need to fill I values. So at I is equal to position is equal to 0, what is your I value? So position is equal to 0, what is your I value in the sense? Here, at position is equal to 0, your I values. So whatever is here, between +1 and -1, your I value will come. If I is equal to 0, which is for more frequencies, at position is equal to 0, your I value will be something. At position is equal to 1, because this goes, we are not going to consider some curves here, which are like, even if the position is equal to 0 or position is equal to 1, you may get the similar values here. But this will not happen when you go with this more frequency graph, because at position is equal to 0, you get this one, and position at 1, you get some other value. So this is the reason we are going for the more frequency for I values, and though we consider 0, this will get compensated here and you get some values to these positional values. I hope you are clear with how we are filling the P vector. I mean this positional vector. Are you able to understand? Are you able to follow? We get some, these positions means how many number of vocabularies are there. If 100 vocabularies are there, 100 positions will be there on the x-axis. And how many dimensions are there, that many I values, indices will be there. And at I is equal to 1, you get one graph. I is equal to 2, you get another graph. I is equal to 3, and so on. So you get more frequency and less frequency graphs. At any position, if you go for the more frequencies, you can fill that values with the highest frequencies, and with the less frequency, you can fill these values here. So that we are getting a position place where the word actually exists. A word ekkada untadi anedi positions anedi define chestunnanu. Okay. Now the word embedding and the position embedding both gives one value to your word. So that word, nothing but we are calling that to be as a vector. So this gives the word, that value is nothing but the word order here. So this is what is your, now we can fill your at I is equal to 1, 2, 3, 4, 5, your word and the positions, and this you can fill with, you calculate the positions. So for one word here, you get one vector, and for another word, you get another vector, which are all different here. So we have completed the first low-level layer of the vision transformers. So this part we have completed. Just now we have completed this part. Position and this. So this is what is the output of this. Till now we have calculated the last part here. This is what we call that as, from here we have to focus on the word, what is attention, and why we have to do that. Attention here is, whichever is important, whichever is prominent, we call that to be as the attention word. So even if we take like the question, if we take which is the biggest university in AP, among these all words, we first concentrate on the university in AP and then the biggest. The remaining all we are not considering. So the attention goes to very important keywords. So that important keywords, we need, if you can retrieve, first give the highest probability to that words, then the answer will come automatically. So from where the probability comes is from the order what you give. From where the order you get is now from where the calculations we have done with the word and the position orders. So, yeah. And with the transformers, we can take the complete sentence rather than unlike in LSTMs where they take only the less words which are given. Transformers will consider the complete words that we will see when we come to the decoders. Multi-head attention examples. So if not, in this sentence you have 3 words to be as keys, and to that if I add any other sentence. If I add some other sentence where you have to get 2 more attentions, one sentence and the other sentence. So which is 2 attentions you need to pay, and you have to go for the more layers. So if, say for example, if you have this picture, you have only one, and if you focus on one beast, and if someone wants to defend that beast, they can see when it gives the fire out, and whenever that fire out comes from its mouth, then he can have the defense mechanism. Whereas if someone is having 2 beasts here, 2 heads are there, which means your attention has to go for 2 heads. Your attention has to defend this as well as this. So 2 attentions you have to pay, which we call that as multi-head attention. So multi-head attentions, how to deal, and what are the basic math behind that multi-head attentions. So we need to have, that is the layer, that is your multi-head attention. And what we have to see here is, this is the complete part, what happens inside this multi-head attention. 3 parameters we have to learn: query, key, and value. For that multi-head attention to know or to calculate the attention, we need to have the 3 parameters. We quickly see what the 3 parameters are. Self-attention, it is, after self-attention you have the, if you combine your self-attention, you have the multi-head attention. And this is relationship among the words within the same sentence, that is your self-attention. And if you have more number of sentences like that, we call it as multi-head attention. And we need to find the difference between the one example, the bank only. So that bank, you can read that how those 2 banks are different from each other. So if you calculate the vectors are embedding for this, and this will be different, and how this bank is related to this person, and this bank is first related to the river bank. So we need to relate the words like this. Yeah. You have a linear layer starting from this one. We see this part, the initial part is the linear layer, where generally linear layer is nothing but what you see in the neural networks, where they are connected and they directly. This is the part where fully connected, this part here is fully connected. We try to increase or decrease the classes based on the number of the sets or the vocabulary there. This is how you calculate the probabilities. The final calculation is the probabilities if you take any text, because we are dealing with the vectors. Yeah, whichever is with the final highest probability, that will be taken. So when you play the Game of Thrones, so the next word should be generated is U. Even if the decoder generates I, by mistake, from where the decoder generates I, how it will generate I instead of U. Are you able to get my question? Why the decoder generates I when it has to generate U? Why it is generating I? Based on the initial feature values, what we have taken, or sometimes which are taken as randomly, are the wrong ones. Because of that, it has generated I. So you need to change that values. So instead of going back and changing the values, like in neural networks, changing the bias values or the weight values, here we directly give the I instead of U instead of I. So we are not taking the value of I, even if the decoder generates I. So the next word which will be given to the decoder is U instead of I. So when it is given, so this is the word. So this has to generate you win or you die. That is the end word. So when we are giving this again, that I, because that is the input to the decoder. So what is the two inputs to the decoder is the output, what it has to be generated will be the input, you win or die. That is one. And the other input is whatever is generated from itself. So for that you have to calculate again E, and P positions to that word. So you win or die. For that three words also, E and P are to be calculated. Example for your masked multi-letter attention. So these are the half sentences and the remaining sentences what they have to be completed. It is understood that again, because this is the training data, both are fed into the system. Both are fed into the transformer. Yeah. Once you give this as input, encoder and decoder, the output what you should get is, this is an example for another sentence, you fool, I kill you, or no man can kill me. So the output what you should get is and no man. So what happens here, the masking, just the masking which we left previously is, simply I tell is because it's not a labeled data, because we are not specifying that this is the class. We did not give anything as the labeled data. All the words we have given as the classes. So what the decoder wants or what the transformer wants is two words should not have the same rank. So for that, it doesn't want the future words to predict as the importance. So until a sentence, full sentence, when you have the full sentence here, when it is at this particular point, this don't want this word to be generated as the important. Until no man can kill me. If you take the V by V matrix in that, when you are at no, the next word should come as man. Kill should not come. So to mask that kill, the encoder gives all the negative values to the matrix here. So to all these values are given some negative values. And this is given look-ahead matrix. For this look-ahead matrix, these values are zeros and the remaining are given as the negative values. So what actually comes is the low matrix is important. So to that lower matrix, if you add this scale scores, like similar to your attention scores, here you are having scaled scores, same values. So to that, you are adding this look ahead. So to the minus infinity, even if you add something, they will be infinite values only, and whatever values are this side will come the lower right hand. And to this, you normalize them. So when you normalize them, all the infinity values will become 0. So which means that the future words probabilities are becoming zeros. Yeah, so I am fine and I am fine, these are the values, and to that it will softmax this, and you are making the remaining future words as zeros, and you will be left over with the only one word which is the future word, and that probability will be here. So this is what is your encoder is. So that we call that as making the words masking, we call that as teacher forcing. So which we are trying to recover from its own mistakes. We are not making the mistake to continue, but we give the hint. So the hint will be the right word. Yes, so just the recap of this is masking before the softmax. So before the softmax, you give the masked values and you make this matrix move by applying so many layers, just multiplications only, that's it. So here, so these are all with this example, masking values, same example. So this is the way how the masked attention phase is. Once you give the input, these are all the inputs here, and you give the output words with the vectors, even if they generate the wrong values. So when you want to generate I am, the input considered is the whole thing. Full, no man can kill me, I will be the input for the next iteration. So for the next iteration here, when it wants to predict am, so the whole thing will be the input. So it takes the complete word. And when it has to predict no, from this part, the whole thing will be the input. So this is what is the decoder, because it has the order of the words. It will not get confused, and it will give the same order. Output will be in the sequence order. So these are the conclusions here. Vision transformers, this is the architecture of what a transformer is. Vision transformer almost the same thing will be there, except they make the images into patches. So when you make the patch, you need to consider what is the size of that patch and how you are moving your stride. Similar to your deep learning CNN, how you make the strides move onto the image so that they are not overlapping, and keep all that patches linearly, flatten them, and again give it to your encoder, the transformer I should say. So this is what, this is not the right picture. Anyway, answer. Okay, this is, there is some other picture. If you make this picture into patches and these patches are given, again the linear projection and position embedding, this totally will be your transformer block, and again patch embeddings give your linear neural network and give the classification. Vision transformer is also like with respect to your images. So the new terms you will be learning is patches, striding, flattening. These are the words you will be learning. And when you go for the Python, it uses or tries to create the tensors out of it. So these are what the tensors, nothing but the values, the kind of vectors. Combine the vectors, call that as a tensor. So examples of your tensors here. Snippets of the code in the Python. I'll try to show the, before the vision you have Python. If you see that, scroll change. These are the, if you go for the Python code, if you're given a sentence is given, how that sentence can be completed. We're not focusing on the Python language here, but you see the words or the packages or the libraries what we are using here. The main thing is in the Python, immediately you should call, when you're using the transformers, you should call the transformer. That is more important. The package, and see all that yeah, see this one is this is what we have worked here. What is the fastest car? The input is given, what is the fastest car in the, and we left. So the world is the output from the transformer. So how this transformer has what is torch, and we have to install these transformers. As I said, like GPT are having so many versions, so we have taken GPT-2 tokenizer, and it takes that word, tokenizes that. Tokenization is nothing but what we have seen here as embeddings. So tokenization is nothing but the embeddings. So that embeddings are done, and in the, yeah, this is what is encoding with single word, with encode as one of the methods and decode as one of the methods. We have generated the word as the word. This is the predicted text here. The input is given as what is the fastest car in the, and the output is the word. That is the output it has generated. Simple thing is the word, what we have taken here as all that K, Q, K and V values, everything is embedded in your encode method. And the decode method has your masking, multi-head attention, everything is in your decode. So this is one example. I do have vision transformers, and here I stop for my friend to continue. Vision transformers, there is one example in my system. Instead of Python, even I recommend all of you to go with the Colab. We need not go for any installations. Simply we get all the packages from the cloud and simple execution we can do. So with the basic thing, what happens inside the transformers, the only thing we do in the coding is if you just know what are the methods and the packages or the libraries, what we call, we can code. So this is what the logic behind the transformers. And as like, I don't know why in our academics still the transformers concept is not included in our subjects, but this is very, very important. Why people are going for this is whatever the CNN does, the same thing transformers will do, definitely. But there is no difference. Only the thing, the difference comes here is when the input is huge, input is very, very large, transformer gives more accuracy, more efficient and more accuracy than the CNNs. So this is what is your transformers concept. Vision transformers, similar like this. We will see that example with my system. System getting fast. 1 minute then. Just. Vision transformers here, when we say the vision transformers, any image, you can make it into pieces. So that piece we call it as patch, and what is the size of that patch depends on the striding. As you know in CNN, when we make the striding or when we divide our image, we make the striding. So you have to define the stride in such a way that any patch should not overlap the other patch. So again, make the patch into the vector. The same you repeat. Make the patch, make it a vector, send it into the transformer, make the position embeddings, and only the thing is you have one more layer in vision transformers is MLP, multi-layer perceptrons. So in that multi-layer perceptrons, there you make all the headings of that word and feed it into your decoder. Go with the classification.
With all the administrative responsibilities, how Madam is able to take up the recent topic and share her insights, thoughts. Thank you, Madam, and thanks to Himani Madam also. I'm a bit behind. I have the update.
Give it as an input.
Madam, in the striding itself, you give the denoise. That is what, yeah. And vision encoder model or VAT image processor, GPU tokenizer fast, simply calling from the transformers package. And here somewhere you have to mention the sizes of your striding should be there. I think I have seen in some other tokenizers. I have seen in some other code, Madam, you have to mention the size of the stride of image and stride so that they not overlap. This is somewhat advanced code where I am trying to download this image and just downloading this image and trying to do the summarization of that image. So if you give this here, image processor and model generate batch, decode and everything. So after you display that image, after you display this image, what is that we are asking is get caption of this image. So that is the final output we are giving to the transformer by making all that image processing and tokenizer. And the output you get is this one, black horse running through a grassy field. This is the summarization, image caption, is one example. So as this Python, it calls all, but we are not focusing on the Python, but the words what we see is what we see in the architecture, so that we understand the architecture, the working of that architecture and the code related. Thank you.